So Naveen, you have to sync with CJ.
Yes, sir. Yes.
Some problem with his laptop. Naveen, you have
Okay.
to CJ, you have to get it sorted out today.
Yes, sir. Yes, sir. Good afternoon, everyone. I hope I'm audible. Naveen, am I audible?
Yes, sir, Joe, you are audible. You are audible.
Yeah,
Yes, yes. Thank you, thank
yeah.
you. Yeah. So we have had a quick glance into how the GM by AD technique works and how to make use of GM by AD technique, taking into consideration for the design of CS amplifier. Also, we have gone through some theoretical background on the MOSFET differential amplifier, how the differential signaling help us to reject the common mode noise, and also we have touched to 7-pack op-amp design also. So mainly in this session, we are looking for an illustrative design of a CS amplifier with a resistive load using Cadence tool. So to begin with, let me give you the specification for the CS amplifier design. So we are having the specification as below, as given in the slide, as you can see. So we are having a supply voltage for 3.3 volt. So basically we are designing this for using GPDK 180 nanometer technology node, and we are looking for a gain magnitude greater than or equal to 5, and we have a load resistance that is named as R load here as 5 kilo ohms, and we are looking for a balanced output swing at the output for the faithful amplification. So we are taking the output potential at VDD by 2, and also the power dissipation factor I missed to specify here. So the power dissipation is actually less than or equal to 1 milliwatts. Okay, so if you move to the next slide, Navi. Yeah, so coming to the design approach, we have given the gain. So we all know the gain of a common source stage as GM into R out. So R out here is basically the output resistance, okay, of your MOSFET. So here the input device is NMOS, so output resistance of your MOSFET in parallel with the load resistance RL. Okay, so RL here as per the specification is 5 kilo ohms, and also uh, the GM. So GM actually, so the power dissipation is given as 1 milliwatt here. So if we know the RL value and the power dissipation, we can find the ID here. So ID is turned out to be what is 1 milliamps divided by 3.3, so that will come around 300 microamps. Also you can find ID since RL is given here, and also we have mentioned for the faithful amplification at the output node we are looking for a output DC potential of VDD by 2. So taking that into consideration, also you can find your supply is 3.3, that is VDD is 3.3 volt. So we can find ID as 1.65 by 5K, that also comes to 300 microamps. So from the power dissipation part itself, you can find what is the ID. Okay. Okay, so now coming to the GM. So as you can see in the gain equation, that's a small signal DC gain, it is GM into R out. So R out is actually R out in parallel with the load resistance. So R out usually for the MOSFET, it can be very high compared to the physical load resistance RL, whatever we are attaching. So when we take the parallel combination of R out in parallel with RL, your effective R out will be mostly dominated by the load resistance. So I can just simplify the gain equation as GM into RL approximately. So taking that into consideration, you can find GM is equal to whatever the gain from the spec, that is 5, gain magnitude is 5 divided by 5K, it will give you 1 millisiemens as the GM value. So now we are looking for the GM by ID technique. So what is the GM by ID value here from the derived parameters? So from the derived parameters, GM we already got it as 1 millisiemens, and ID is 300 microamps from the power dissipation specification. So from that we can find the GM by ID ratio here is 3.3. Okay, so this much things we have calculated. So now we need to find for this much GM by ID, okay, what is my current density, that is what I'm going to plot. Also taking into consideration that my MOSFET is working in moderate or weak inversion. Okay, so we'll now look into go to the NMOS characterization, and we'll find out how to characterize the NMOS to extract these DC operating point parameters such as GM, ID, R out, CGG, CDD, all of the things what are we discussed now. So all those things, how we can extract those parameters across different value of VGS, that is varying VGS. Okay, so we'll look at the test setup for that characterization part first, then we'll come back to the design approach. Okay, so Naveen.
1 minute, CJ.
Yeah.
Sorry to interrupt. Yeah, just to summarize for the benefit of participants who are perhaps looking at this approach for the first time. So what actually we did actually is we spoke about GM by ID technique and very brief insight into it. We said in the specific session, even session, that we need to characterize the devices to generate these curves or lookup tables. right, for all those small signal parameters of interest. So here actually we just pick up arbitrary design specifications. It starts with a very simple story, where we have a passive resistive load in a common source amplifier. We define load within gain actually as pi. And as you rightly mentioned, the small signal resistance R out, small R out up there, is in there, right, is large compared to the external passive load resistance, which is just about 5K. Parallel combination turns out to be equal to RL itself. And then we compute what is the value of GM we require. So first of all, we are setting up a lower bound limit for GM. So GM has to be equal to or greater than whatever value you are actually going to see here as 1 millisieverts, right? And then ID, yes, C2 has indicated calculation in terms of quiescent drain potential, right, as VDD by 2. And because RL is given, we computed ID from that, right? Then we know GM from the required gain, and we know ID from either the power dissipation or the quiescent drain voltage. Now we figure out what must be the smallest minimum value of GM over ID. So this is the smallest value I get, 3.3. Now what we do actually is, all right, we have a couple of references. GMI require minimum 1 millisiemens. GMI ID minimum I require actually is 3.3. So now we go ahead, characterize the devices for 3 different values of length, right? So 1.65 HD is VDD by 2. VDD HD is 3.3 volts. And in the specifications, it's already specified that V out under quiescent conditions is to be VDD by 2. So 1.65 is 3.3 by 2. All right. And because half this supply voltage has to be dropped under quiescent conditions across RL, right, is why CJ actually is computing what must be ID in that load resistance. So this is a common source amplifier with a passive load resistance of 5 kilo ohms. Am I clear? So now he will actually illustrate with help from Naveen, right? How do we do the setup for characterizing the devices, the NMOS device in this case, right? For extracting curves of GM, ID, GM over ID, FT, that is the transit frequency, right? Then CDD, CGG, CGS, and CGD. First step is that, right? So for this, he'll go to the tool and set up an operating point analysis for the N MOSFET. Naveen, please go ahead.
Naveen, can you open that NMOS? Yeah. Yeah. So this is the test setup for NMOS characterization. So I'm just connecting a DC voltage source at the gate terminal, and I'm connecting another DC voltage source across my VDS. So source is in ground. So whatever the VD is the VDS of my transistor, and also whatever the gate voltage VG, which I have named as a variable, defined as a variable here, that is the VGS of the MOSFET. Okay, so this is the test setup for NMOS characterization. So now we will look into the simulation part of it. So what you can do is, this is actually the Virtuoso schematic editor window. From here, basically, you can launch. Okay, Naveen, can you just show that? Yeah, you can launch ADL window for the further simulation. So ADL means unlock design environment. Okay, so for the time being, we already have the saved state available. So we will quickly bring you to the saved state. Okay, so Naveen, yeah, no need to open it, already opened it, right? ADXL window, you can close. Yeah, open that ADXL window, already open. Yeah, so for that, since it takes bit time for the characterization, because it is running more than 300 points, so it will take some time. So we are actually telling you how to set up the simulation for the NMOS characterization. Okay, we will not be running the simulation now because it takes some time, so we will quickly tell you how to do the simulation. So basically we are running a DC operating point analysis. So if you look into this, Naveen, can you open that test in interactive 7 test? Yeah, and again inside that, yeah, can you open that global variable parts also? Yeah, yeah. So here, as you can see, I have defined the length of the MOSFET L as 0.18 U or 180 nanometer, and W I have given 5 U, and VG, that is the gate to source potential, I am varying from 0 to 3.3. So actually speaking, we were actually characterizing it for different values of L as VDS are mentioned in the previous session. So we'll be characterizing it for 0.18 U, then 0.5 U, and also we can have one more higher value as 1U. But as our aim is to get the maximum bandwidth or gain bandwidth for the design, we are actually going with minimum L, so that saves our simulation time. Okay, if you have some other application, then you can also set more values for L, so that accordingly more curves will be generated. Okay, so for the time being, since our aim is to get the maximum bandwidth, we are going for minimum L, that is for 180 nanometer technology, it is 180 nanometer or 0.18 U. So I have defined L as 0.18 U and W as 5 U. Okay, and VG we are sweeping across 0 to 3.3, okay, with a step size of 0.01 volts. Okay, and drain to source potential, that is a VD, which we have defined in the schematic. I'm keeping it as VDD by 2, that is 3.3 by 2, that is 1.65 volt. Okay, and coming to the corner, can you open that corner, Navi? Yeah. So in GPDK, mainly you have nominal, slow, slow, fast, fast. Then you have slow, fast, fast, slow, all the corners. And also you can define extra corners. Okay. So we are actually doing the design for the nominal corner. So I have enabled nominal corner here. Okay. So this is the simulation setup, and actually we are running a DC operating point analysis. So if you look at the output setup, Naveen, can you click on that output setup? Output setup, just left to the left of results, and on the right top, just next to the result. Yeah, so in the, these are the DC operating point parameters which I am plotting here. The main things I am plotting are GM ID, GM over ID. Okay, self gain, that is the intrinsic gain of the MOSFET, GM into R out. Then CDD, CGG, R out, FUG, that is the FT of the transistor, and the VD, VDS value at VD sat value, that's VD sat. Okay, so these are the main DC operating point parameters I am plotting. Okay, for different value of VG starting from 0 to 3.3 volts for a step size of 0.03. Okay, so if you plot it, as you can see the results. Naveen, can you show the results? Yeah, so once the simulation is done, you can find for it has generated 331 sweeps. Okay, and for each value of VG, okay, starting from 0 with an increment of 0.01 volt, it will tell you what are the different values for 9 DC operating point parameters which you already defined in the output setup. Okay, now you have the plot option here. Okay, you can see a graph kind of an icon. Okay, so if you click there, you have plot all option. We have already plotted the graphs here, so we can directly open the graphs and show it to you. Okay, so yeah, so as you can see, we have GM ID on the left side of the graph. You can see it is listed which all the DC operating point parameters it is plotting. So it is GM ID, GM over ID, and you have the intrinsic gain of the MOSFET, and you have CDD, CGG. So CDD is the effective capacitance at the drain terminal, CGG is the effective capacitance at the gate terminal. Then you have FUG or FT of the transistor. Okay, you have the R out, okay, of the transistor, and also you have VD sat. Okay, for a W of 5U and L is equal to L minimum, that is 180 nanometer. Okay, so if you look into the slides, okay, we got GM by ID as 3.3. So I can go to the GM curve first. So if you look at the GM curve, Naveen, can you open the GM curve? So, GM by ID curve, sorry, GM by ID curve. Yeah. So if you look at the GM by ID curve, so we have got the GM by ID ratio as 3.3. So you can put a horizontal cursor in the graph and you can set the value as 3.3. And if you look at the corresponding VGS value here, we are getting it as 937.31 millivolts. Okay. So are we good to go with this GM by ID value, or uh, should we reconsider the GM by ID value? So how we will decide upon this? So as I already told, I want my input transistor or the input NMOS to be in weak or moderate inversion. So I should check for this value of GM by ID, okay, and for that the particular value of VGS 937 milli, whether my transistor is in weak inversion or strong inversion or moderate inversion, whatever. So my aim is to bring my transistor to weak or moderate inversion. So if you look at the GM curve for that one, so if you open that Windows 17, can you open that Windows 17, Naveen, just before GM curve? Yeah. So this is the GM curve. So if you put the cursor at 930, okay, that is a cursor which is highlighted, 930 millivolts, you can see, okay, your GM is almost in strong inversion. It is almost touching that saturation region. So I want to bring my MOSFET to weak inversion. That is, in the linear curve, you can see in the GM curve, you have the linear portion. Okay. So what we will do is we will reconsider the GM by ID value so that I can bring my MOSFET in weak or moderate inversion and I can carry forward the design. So coming back to the slide, Naveen, can you come back to the slide, please? Yeah, next slide. Yeah. So this is the GM by ID curve. Okay. So for GM by ID for 3.3, we already noted the VGS value. For that VGS value, if you look at the GM curve, we already noted that it is in strong inversion. So what we can do is we can reconsider the GM by ID value. So for the first cut approximation, if you move to the next slide, Avi. Yeah. So this is the GM curve which we noted for the corresponding value of VGS, okay, of 937. So as we have seen from the graph, it is already in strong inversion. So we are actually reconsidering the GM by ID. So we are looking for a larger GM by ID, okay, so that your transistor can come to weak inversion or moderate inversion. So for first cut approximation, we are going with GM by ID. We are taking 3 times of the value whatever we got. So it is 3.3 now. We are going for almost 9.9, around 10. So now we can reconsider the GM by ID value of 10, and we can see the GM curve, and let's see whether the transistor is in strong inversion itself or is it coming back to moderate inversion. Okay, so that is what we are going. So if you look at the graph again, Navi, in the tool. Yeah. So what I am trying to do is, if you look at the GM by ID curve, GM by ID curve, please. Yeah. So I will set that horizontal cursor to 10. That is what the new value we are trying. So Naveen, can you put 10 there? Yeah. So at 10, we are getting a VGS value of 661.72. So almost equal to 662 millivolts. So if you look at this value of VGS, let's look at the GM curve. That is the previous graph. And let's put a cursor at 662 millivolts. And we can see it is already in that moderate inversion. It has come down from strong inversion to moderate inversion. So how the higher the GM by ID value, how the transistor will come to moderate inversion? Because if you increase the GM by ID value means, okay, that is if you are that means ID value you are reducing. So you can see in the moderate inversion, that is in the linear region, the ID value is very less. So for a particular value of GM, ID is very small, so that GM by ID value obviously will tend to a higher value compared to the GM by ID value in the strong inversion. So that is how when we increase the GM by ID 3 times, okay, when we increase the GM by ID value 3 times the GM by ID value of 3.3, we are able to bring the MOSFET into moderate inversion. So now we are fixing the VGS as 662 for a GM by ID of 10. Okay. So now the next thing is, now we got the GM by ID value, okay, as 10. So for that one, we should see, as VDS are already denoted, GM by ID value is independent of W. So we should see, now L we have fixed, we have gone with L as L minimum, that is 180 nanometer. Okay, now we should see what is the self gain and FUG. Okay, so that if we have a requirement of small signal gain of 5, so for this particular value of GM by ID, if I am able to have a, okay, FUG or intrinsic gain, self gain greater than what is the circuit requirement of 5, we are actually good to go. Also the same applies to the FUG of the MOSFET. So if you are getting a, by the rule of thumb, if you are getting a 50 times larger value for the FUG, okay, from the system requirement, you are also good to go with that value. So now we'll quickly plot GM by ID, okay, across the self gain of the NMOS device. So that what you should do is, you can come to the first plot, Navi. Yeah, you can choose GM by ID curve, right click, yeah, you can copy to a new window. Okay, so this is VGS across GM by ID. Now I am trying to plot self gain across GM by ID. So what you should do is, you can again go to, yeah, you can select self gain, you can copy and paste it in the same window. Okay, yeah, so now you have GM by ID and self gain, that is the y axis here, and x axis is VG. So now we are trying to plot GM by ID across self gain. So here in Cadence we have an option to plot y versus y. So if you go to the axis, you have y versus y option. If you select that, okay, so now if you can select GM by ID, so whatever the value you choose, that will be your x axis. So I want GM by ID in the x axis. You click OK. Okay, so now you got the curve for self gain versus GM over ID. Okay, so for better resolution, you can send to a new window. Okay, you can put a cursor, okay, vertical cursor for the calculated GM by ID, that is 10. So if you put the cursor to 10, yeah, you are getting a self gain of 49. Okay, so whatever the gain requirement for the circuit is 5, gain magnitude is 5, so we are anyway a decade away from that one, so we are good to go. Okay, so
Yeah, let me interrupt you here. So
yes,
just to quickly summarize what you try to illustrate up here is, we computed what is the minimum GM we require from the design specifications. We also computed what is maximum ID that is allowed based on the power dissipation as well as the quiescent output node voltage specified, right? So those values we computed, what is the smallest GM ID we should be working with. Then we showed the setup for generating those curves. Honestly speaking, we typically parameterize L for at least 3 to 10 values, depending on things, depending on the requirements. Just for the sake of, for the want of time here, to say simulation run times, we have shown it only for one particular length, right? And then generated the curves. So from the GM curves and GM over ID curves, right? We actually tried figuring out from GM over ID curve for 3.3 what will be the gate potential, and for that gate potential attempted to figure out whether the MOSFET will be in strong inversion, weak inversion, or moderate inversion. As I already said in the pre-lunch session, larger value of GM over ID essentially means that we actually get larger voltage swings and therefore and smaller overdrive voltages, that is minimum VDSs across transistors as potential headroom under bias conditions, right? And maybe a smaller value of FD, right? So we actually found out there from GM curves that the device here turns out to be closer to strong inversion than in weak or moderate inversion. We prefer to work amplifying devices in weak or moderate inversion basically because we get large GM at a lower power dissipation, right, by using a smaller value of ID. Hence, we hike the GM by ID value from the required minimum 3.3 to approximately size step, that actually is 10. So for GM over ID of 10, we actually figured out that looking at GM curve, the MOSFET is indeed in moderate inversion. And having done so, next what actually needs to be done is to figure out whether the MOSFET self gain, which is the maximum gain achievable by the MOSFET if other components of the circuits are all ideal, right? So whether that intrinsic gain of the MOSFET is large enough compared to the required circuit gain. If the required circuit gain is 5, the intrinsic gain here, right, is is obtained actually as almost 50 at the chosen value of GM over ID. That means the intrinsic gain of the MOSFET as a device, right, is practically 10 times the overall circuit gain required, so looks like achievable. At times we bump into situations which doesn't look like achievable. We may have to run more number of curves and then iterate a lot. Right? So this actually is satisfied. Next, what we need to look actually is what is the typical bandwidth that might be achievable. Right now, bandwidth specification is not given in this particular design spec. We just like to maximize the bandwidth while achieving the required specified gain, right? So to maximize bandwidth, we recognize that bandwidth expressed in terms of like your cutoff frequencies and in radians per second, omega. Omega is always equal to reciprocal of the time constant that defines the pole in a transfer function, right? So given that particular case, what we find is that in order to maximize the bandwidth, we need to minimize the time constants that define the bandwidth, right? That defines the pole locations. To minimize the bandwidth, we require smaller RC time constants. And the load specified here is not mentioned in the design specifications. It is about 500 femtofarads, right? So at load capacitance of 500 femtofarads, to maximize the bandwidth, I would like to keep the effective time constant, right, between the drain and the source in the output circuit as small as possible. And therefore, we are choosing L equal to L minimum, which is 180 nanometers. So now next what we check is for the desired chosen value of GM over ID, what will be the transit frequency of the MOSFET? So he's plotting FT versus GM over ID. Naveen, can you quickly do that? FT versus GM over ID. Or if you have the curve already, then GM over ID. All right. So set up GM over ID vertical cursor of 10. Okay. So we get the FT value as approximately 26 gigahertz. Right? So what actually does it mean? If I now pick this MOSFET, size it up, we'll come to how do I set up the W value. Right? We have fixed up L, we have fixed up VGS, choosing GM over ID greater than the minimum required value. Right? And then looked at self gain. Looks like self gain is large enough compared to the required circuit gain. Now we are looking at FT of the MOSFET, right? So what actually tells us is that depending the overall circuit bandwidth I get, maximum bandwidth I get at unity gain will always be much smaller than the FT of the transistor as explained in the previous session. Right? So what I find actually is that FT of the transistor is large enough, it's almost 26 gigahertz. Right? So what actually all this means is that if I size W, connect this transistor in common source amplifier with an ideal load resistance RL, right? And work this up, I should be actually able to get a maximum bandwidth of 26 gigahertz. That's what actually it gets, right? So now having done this, let us next plot the current density ID by W, right, versus GM over ID. So we have ID here. We have to use calculator and divide this by width of the transistor and plot that curve. The width of the transistor is 5 micron.
Select that waveform. Yeah.
Okay, so now we actually plot this current density versus GM over ID. So please note, current density is ID by W, therefore the current density is again independent of width. GM over ID is independent of width. So we are having current density which is independent of width of the device along y-axis, and GM over ID which again is independent of the width of the device, right, along x-axis. That's the curve we actually plot. Please note, actually we are showing all graphical user interface clicks up here rather than directly running scripts. It is possible to write scripts for each of these curve generations and just use a push button to run the script and generate all the curves in one go. All right, so on the y-axis now we have the current density, right? And then on the x-axis we have GM over ID. So set up a vertical cursor now for GM over ID of 10 and look up what is the current density. So the current density actually is approximately 30 amperes, right? The maximum current that is allowed by the design specification is 300 microamperes. So if I divide the maximum bias current of 300 microamperes, which we calculated from the design specifications, by the current density, we get the value of W. So 300 microamperes by 30 amperes, right, per meter, that actually is the current density value we are reading. So we actually get width as 10 micrometers. 300 microamperes divided by 30 amperes per meter actually is 10 micrometers. So that actually fixes up the device width also. So just to summarize, we now actually have supply voltage 3.3, RL is 5 kilo ohm, right? We characterize the MOSFET to generate all those small signal parameters of interest, right? And then from that, actually chose the value of GM over ID to be larger than the minimum required, right? And then for the chosen value of GM over ID to operate the device in moderate inversion, right? We checked whether the self gain is large enough compared to the required circuit gain. We found out it is, right? Then we checked what is the transit frequency. Is it large enough? It indeed is large enough, right? It's in the range of almost 26 gigahertz. Then we actually plotted the current density of the MOSFET versus GM over ID. And from the current density curve, we actually figured out what must be the W. So now we have all the dimensions of the MOSFET that actually we require. And we know what's the bias voltage required at the gate. That actually is 662 millivolts, as actually is found out for the chosen value of GM over ID equal to 10. Right? So with all this, let us now go ahead and hook up the common source amplifier with this resistive load and check whether we are getting what we actually designed it for. Naveen, Tijo, are we done
Yes, sir.
with
Yes, sir.
this?
Yes,
Yeah.
yes. Naveen, can you open the schematic, please?
Yeah.
Please note, all the professors, we are not actually demonstrating here every mouse click on capturing of schematic, etc., because
We understand that.
we actually have free webinars on tool usage where we actually explain every click. In addition, we can actually also share tutorials that actually tell you how to actually capture a schematic, how to modify a schematic, how to set up your library paths, etc. So that basically actually is tool flow usage and not design flow. So for the want of saving time and coverage, we are not getting into those details. We have free webinars actually available for those things. All right, so here actually we have the setup. So what actually we find here is that Sijo, W is
Yes.
getting different here.
No, sir. I have taken multiplier 4. Naveen, can you correct
Oh,
that
sorry.
CL to 500 femto?
Yeah.
Yeah. So from the
Well,
calculated value, we are getting W of 10 U basically for the MOSFET.
yes. Yeah. So
So
actually, what Sijo actually has done is instantiated a MOSFET with the width of 2.5 microns, length of 180 nanometers, and then connected 4 copies of these MOSFETs in parallel. That effectively makes up total width of 10 microns, as obtained from the current density curve versus GM over I. Is that right, Sijo?
yes, sir. Yes.
All right. So let us just go back to the schematic.
Yeah.
Naveen, you
Naveen,
have to correct the
load
capacitance value, load
500.
capacitance value. It is 500 femtofarads. Sijo forgot to mention that on the slide of design specs. All right. So now what actually you can see here from the simulation setup is, again, Sijo actually forgot to mention the source resistance, which actually is 10K, Sijo, not 100K, R1.
Yes, yes.
There's a mistake there. It is 10K, typo. All right. So we have a similar source resistance of 10K. I already talked in the first session about uh, how exactly is the signal voltage source different from energy voltage source. Typically, a signal voltage source has a much larger resistance than an energy voltage source, right? This perhaps one actually also gets to see when actually you are using a function generator in basic electronics lab. You can actually look at the resistance mentioned there on the front panel. It typically is listed as 600 ohms. It's a routine lab type function generator, right? So here we have VD setup. We have set up the bias voltage in terms of DC voltage V1, right? So there actually it is defined as a parameter value V bias and MOS, right? And then sinusoidal source also actually has been defined, and there is a AC magnitude defined actually as one for the frequency response analysis, which actually can be done for the DC source and or the sinusoidal source as well. It is done here for the DC source, right? So all this is done. So the first analysis we run up actually is the DC operating point analysis to check, first of all, whether the MOSFET is indeed operating in its saturation region in the ID VDS plane. Because if it is not, then it is not working as a voltage controlled current source. First check is that region of operation. Then we check all other small signal parameters as available from this particular MOSFET for this size and the biasing that we have computed. Is that fine? So let us go ahead to the simulation setup. So you can see here the V bias for NMOS is set up as 662 millivolts. Can you take the cursor there, please? Yes, that's it. Right? That was the actual value which we figured out on the simulation course. Right? So now what actually we are doing is first of all carrying out the operating point analysis. In fact, both operating point analysis and the small signal EC analysis are already set up. That's fine. So can you run the simulation, please? Triggered?
Yes, sir. Yes.
Just check if simulation is triggered or not. All right.
Yes, of course.
Check the path. Check the path. CJ, first actually, Naveen, I would like to
Yes,
first illustrate the DC operating point values.
okay, sir.
So print results and point to the transistor to look at the DC operating point results. Okay. So that's a very huge list because over the years, as technology developed, EDA tools also evolved. And since there are designs happening also for the older technology nodes, as a legacy, they have kept whatever was developed over the years as it is. So it is pretty confusing if you look at the huge number of small signal parameters the tool throws up upon DC operating point analysis. Of interest to us are essentially, first of all, the region of operation. Can you check that? Region is 2. So please note that there are basically 4 regions specified by Cadence Spectre Virtuoso, right? Region 2 corresponds to saturation region of operation. Region 1 corresponds to linear region of operation, right? Then region 3, Naveen,
Sir,
region 3
region
corresponds
three,
to
region three is pinch off, and region 0 is cut off.
cutoff. Okay. All right. So it is in region 2, so the MOSFET is indeed in saturation. And now let us actually look at what's the value of ID. Can you look at ID? ID is 328.66 microamperes. So we actually had planned for 300 microamperes. So that we can clearly see here, right, that hand calculations may or may not exactly match the results that actually we have obtained. Because we start with first cut and then we start iterating on the tool by reasoning what's going on, right? ID is in close agreement up there, right? Then we look at GM over ID. That's right, we actually have chosen GM over ID of 10, it is 9.58, very good, right? Then we look at FUG. We measured from the graph there actually before we fixed up W, right, as about 26 gigahertz. It is turning out to 27 gigahertz. That's pretty good. Then self gain. Down. It's there. self gain is turning out to be 48.6. That was just pretty good. All right, and we actually reasoned in our approximation that overall gain at low frequencies is given by Gm into RL, because the small signal output resistance of the MOSFET is generally large, so which turns out to be pretty large. R out here is about 15.4 kilo ohms. Right, so that's an approximation. Okay, right, so all this actually is verified. So now let us go ahead and check, right, what is the quiescent drain voltage. It actually turns out to be about, no, please wait, go back to schematic. Sorry, go back to schematic. Okay, so actually you can see there that the quiescent drain voltage is turning out to be about 1.65809 volts. So it is pretty close to VDD by 2. That also is satisfied, right? So now let us go ahead and run the small signal AC response and check whether we are getting the required gain at all or not. So what CJ is plotting actually is the magnitude and phase plots together. Can you split the graphs to separate the graphs out? Can you just change the trace properties here? Okay. That's okay. Make it solid, that's good enough. And you put a marker. Good. So we actually are getting the overall gain actually as about 27.5 decibels. Right? So if I round it off to, let us say, about 28 decibels, just for quick calculations, that basically means that 28 decibels is 20 log to the base 10 of the numerical gain of the circuit. So the numerical gain of the circuit turns out to be 10 to the power of 28 by 20. That is 1.4. So 10 to the power of 1.4 is how much?
25. 25.
Sorry?
25, sir.
25, sir.
That's a pretty large gain. Hello?
Yes, sir. Yes.
So actually we are getting a gain larger than what actually we designed it for, pretty large. That is because our R out is pretty large also at the same time. Fine. Let us look at the maximum bandwidth at 0 decibels. That's the unity gain crossover frequency. Set up a horizontal cursor there. That turns out to be almost 1.15 gigahertz. So we did not actually plan for how much unity gain bandwidth. We just attempted to maximize that. So we get a large gain, right, and also a large bandwidth. So what actually you find is that if you want to now zero in down to the specified requirements, then you may actually have to go in for more iterations. But right now, as an illustration that the technique really works, right, we'll actually stop it here. So you have any questions, right, please let me know before we proceed. Next, actually, what we are trying to do is to modify this circuit to a common source amplifier with a PMOS active current source load.
Sir, what would be the procedure if there are more than one transistor? Let us assume if the load is also a transistor, then
Exactly, that's the next circuit. That's the next circuit. The next circuit is going to be CS amplifier with a PMOS load. Hello. Okay. All right. So let us, yeah. So let us go ahead, Naveen. Let us go to the slides and modify the specifications. So what I did here actually is to kind of reason it out, right? If I let us say have a PMOS active current source load, what is the achievable gain? Now the NMOS actually has a self gain of about 50 in this circuit for a R out of about 15 or 16 kilo ohms. It exhibits across its drain to source terminals. So if I connect a PMOS carrying the identical current as the NMOS and exhibit a R out which is equal to the R out of NMOS, then the overall gain is going to be GM1 times R01 in parallel with R02, which is already available on the slide. Okay, so if I set R02 equal to R01, then the gain achievable is approximately 1/2 the self gain of M1. And the self gain of M1, the NMOS device in this case, is about 50. So we perhaps actually can achieve a gain pretty close to that. So let us go ahead, right, and then look at the PMOS characterization. So how do we go about? We go the same way. We characterize the PMOS device also exactly the same way. We are again simulating the PMOS device for W equal to 5 micron, L equal to 0.18 micron. We would actually prefer to simulate it for more number of values of lengths, maybe at least another 3, 4, right? Once we do that, right, we are choosing L same as NMOS device, right? And then we actually figure out what must be, which is the region in which we must operate the PMOS device. Now, because the PMOS device actually is to function only as a constant current source, typically we would like to operate it in strong inversion region. Okay, we like to operate it in strong inversion region. That means what? In strong inversion, if you look at the GM curve, right, GM is almost hitting its maximum value. However, strong inversion also basically means that I'll be operating at a large value of Vg. That means my overdrive voltage also is large, and therefore the voltage swing available across that will be small. So as a result, what we have done right now actually is to choose to operate the PMOS device also, right, exactly at the same value of Gm over Id. And we plot the same curves. And using this value of Gm over Id, we find out, right, what must be the value of W for the PMOS device, having characterized the PMOS device, right? So, procedure, do we have those curves?
Yes, sir. Yes. I mean, can you go to the tool? PMOS Cara.
Go to the tool.
In Cara library, PMOS Cara.
All right, so that's set up for simulating the PMOS curves. All right, one piece of suggestion up here for NMOS, all the potential differences between the terminals and the drain current are positive values. For PMOS, all these are negative values. So it is good while reading out these graphs or values to generate curves for the PMOS also that actually happen to appear in the first quadrant of your graph sheets. That basically means that in place of drain to source voltage, read source to drain voltage. In place of gate to source voltage, read source to gate voltage. And in place of plotting ID, you plot IS, the source terminal current. Everything remains the same. You are handling everything in terms of magnitudes. I hope I made sense. Right? So we have these curves already available. When you load these curves, you can just load GM over ID curve for 0.18 micron, and against that you plot current density curve.
Yeah, the final slide, final one, yeah.
Okay, so here what CJ has actually done is, instead of reading source terminal current, here red drain terminal current. So the graph actually is looking kind of, turned. Okay, so from CM over ID value of 10, I actually get current density as approximately 8. Forget that negative sign. I'm getting negative sign there in the graph because CJ has plotted ID rather than IS. You can actually see that here, right? All y-axis numbers are negative. Okay, right? Now, because the current is already known to us, it's the same current actually we are operating for, that is 300 microamperes. So 300 microamperes divided by 8.135, right, is approximately coming to how much?
40 U.
40 U, right? So the PMOS width actually we get as 40 U, right? And the gate to source potential difference for the PMOS will be same as that for the NMOS, because actually we have chosen the same GM over ID. All right, so let us go ahead to the, so I guess I answered the query, like, how do I fix things if I have more number of transistors? This actually becomes clearer as we go to the last circuit, that is designing an operational amplifier, straightforward. But there, we don't look at the gain value, we are actually going to look at the bandwidth requirement. So we again use the same approach, but our parameter of interest actually is the unity gain crossover frequency of the op-amp, right? Apart from its DC gain, small signal DC gain, right? So let us open the schematic for common source amplifier with this PMOS current source node. Can you zoom in, please, into the schematics first? No, you zoomed in too much. I just would like to see the two circuits. Okay, so actually we have here two copies of the same circuit, right? I'll tell you what actually we are trying to do here. So the first circuit on the left you get to see on the screen on the tool actually is the common source amplifier with NMOS as our active device and PMOS as the current source load. So as actually you can see here, we have kept the dimensions, biasing, etc. identical for the NMOS device. PMOS width actually is 40 microns, right? So this first circuit actually on the left actually is using PMOS device actually as the active current source load. On the right, we have exactly the same copy of the circuit, but we swap the input and the bias. So the PMOS actually in this case is working as active device, whereas NMOS is working actually as the current source load on the common source amplifier with PMOS as the active device. So actually we are simulating both. All right, so can you just show the simulation setup there? Slightly zoom
Yes,
out
sir.
and let us look at the, no, let us look at the voltage sources and setup connections in the schematic. Zoom out a little. Okay, so zoom in a little more there. All right, so that's what actually you get to see here. V bias 1 is for the N MOSFET, right? Then V bias actually is for the P MOSFET. So 3.3 volts minus 662 millivolts of VSG for the PMOS, right? A slight adjustment there actually gets you 2.75. A little bit of adjustment might be required to help the tool to kind of, converge, right? Please note that all these tools essentially work on numerical integration. Okay, so rest all actually remains the same. So let us go ahead and simulate the circuits and look at both DC operating point values as well as DC responses. Corner, in your corner, I mean, corner did you choose properly? first circuit. Okay, that's what CMOS we are looking at. Just look at what is ID. Okay, slightly reduced. Fine. Then look at what is GM over ID. It's 10.96, slightly higher. Fine. Look at what is GM. It is about 3 milli. Okay, so look up what is FUG. That's about 7 gigahertz, so pretty large. Because frequency response requirement is not specified in our problem. Right, so that's good enough. So now let us look at for both circuits, DC operating point actually will be the same because it's identical problem. Let us run the AC response. Do only one. Do only for the left one. Do only for the left one. Route 10. Okay. So we actually are getting about 28.22 decibels. Alright, so in the design specifications, all that we did actually is to look at the fact that if I connect a PMOS load with Rout comparable to that of NMOS, then I should be able to achieve roughly half of the self gain of NMOS. So that's what actually we are able to get. Alright, so can you just look at also the unity crossover frequency here? That's right, about 606 megahertz. Right, so what really is more interesting is if I just go back to the previous circuit or even this circuit, by reading off the capacitance values from the small signal parameter listing given out by the tool upon operating point analysis, can I do some quick hand calculations to figure out where are the locations of the poles and the zeros? See, do we have that calculation table?
Yes, sir. Yes, sir.
All right.
Naveen, can you open that CSV file?
Yeah.
This is done for the previous circuit or this circuit?
For both it is.
Okay. So which one are you looking at now? Let us look at this circuit.
Okay.
Now let us load the other one, the present one. Let us look at the present one.
Yeah, first one.
All right. So the
This one.
CS amplifier with current source load. Okay. So we have just listed up all the DC operating point parameter values for the transistors, right, up here in field E of the spreadsheet. RL, okay, fine. Okay, and then we have the performance parameters. So AV naught actually is given by now GM of the NMOS device multiplied by the parallel combination of Rout PMOS and Rout NMOS, right? And this value turns out to be equal to 25 from the calculations, right? So we are picking up those values from here from field E. Okay, then C1 is CGS, right, of the NMOS device. So that actually is turning out to be about, how much is this? 122 femtofarads. No, 0.122 femtofarads. No, 122 femtofarads, sorry. Right, this is how much? Okay. Right, then C2, right, is the output port capacitance that turns out to be equal to CL plus CDB of the NMOS, CDB of the PMOS, and we have the value actually picked up from there by picking up the CL value is given as 500 Fem2. TDB of NM0 is available from the corresponding devices parameter output list. Right. Then similarly for the PMOS also we actually have the value available up there. So all that actually added. T3 is the gate to drain capacitance of the NMOS, which is the active device for the first circuit. Right. Then because this is a two-pole transfer function, please note that the input stimulus source has resistance which is reasonably large. Right. So the circuit actually exhibits two time constants essentially, one for the input circuit, one for the output circuit. And the input circuit time constant is given by the sum of the time constants associated with the capacitances at input as well as at the output. So that actually we are listing it actually in the form of denominator polynomial, which is 1 plus b1s plus b2s squared. Right? Those of you who perhaps are little confused on this may please look up any book on frequency response analysis of amplifiers, right? And what actually I'm talking about actually is the dominant pole approximation expressions. All right, so I can actually express the overall transfer function gain for a two-pole transfer function amplifier as AV is equal to AV naught, where AV naught is the small signal DC gain multiplied by 1 minus S divided by omega z, brackets closed, with the RHP 0, then divided by the polynomial in S, which is in the form of 1 plus B1S plus B2S squared. And B1 is simply equal to the sum of the time constants associated with every independent capacitor in the network. So if I loosely say apply Miller's theorem for CGD, which actually is C3 here for the NMOS device, then as you can actually see, CGD appears in parallel with C1, which is CGS of the NMOS device, and therefore the resistance seen by this parallel combination of this, right, is equal to the source resistance. And please note that CGD is appearing as a magnified capacitance across the input port due to Miller effect, 1 plus AV naught, right? And the other one actually is at the output port where C2 is added with C3. C3 is again CGD. So Miller effect is almost same as CGD at the output. So that multiplied by RL. So that actually gives me B1. Similarly, B2 is sum of products of time constants as seen by each of the independent capacitances. Right? So that's what actually is the expression. So that's what actually we calculate. Then we calculate what is the first pole frequency, dominant pole frequency using dominant pole approximation with this simplified transfer function expression as 1 by B1. So many radians per second. And therefore, we actually get FP1 as approximately how much season? FP1.
Yes.
Now, all right.
Yeah.
That's about
22 megahertz. 22 megahertz.
Sorry?
22 megahertz.
22 megahertz. Right? And similarly, FP2 is computed actually as we have the expression for omega P2 as B1 by B2. And from there, I actually get it as non-dominant pole, right? Which
0.9 gigahertz.
0.9 gigahertz, right? We can also compute the frequency at which the RHP0 appears, and that actually is at much higher frequency.
131 gigahertz.
Right? Then actually you can also compute what is the gain bandwidth product. Please note that for a single pole transfer function, the gain bandwidth product is a constant. So if I increase the gain by a factor k, then the bandwidth reduces by a factor k, etc. Right? So we have computed this also, because once I have the dominant pole approximation, essentially it means that the non-dominant pole is at least 2 octaves above the dominant pole. So an octave on the frequency scale is a factor of 2. So the first non-dominant pole is at least, at a frequency 4 times greater than that for the dominant pole, in which case the overall transfer function looks like a single pole transfer function predominantly. And that exactly is where I can actually compute omega UG or FUG the voltage gain bandwidth product, right, as equal to the
600
voltage gain, right, multiplied by the 3 dB bandwidth, which is omega P1 or FP1. So I get FPG as so much,
600
right?
megahertz.
Yeah. And then we can also compute what is the phase of the gain, right? And this actually is loop gain phase actually, like, we are actually plotting, calculating up here in terms of that expression. So if you write the expression for the angle generated by the gain of the amplifier, assuming the feedback factor, if I use this amplifier in a negative feedback system, feedback factor to be purely resistive, then I get argument of beta A, right, simply as argument of A from this transfer function. And that's the expression I get. And correspondingly, therefore, I can compute what is the phase margin in terms of degrees. Okay, so we actually get a phase margin of about 62.6 degrees up here, right? So let us just check one thing. We'll just go to this particular amplifier schematic and carry out a pole zero analysis, which is available on the tool. In fact, it's available on any generic circuit simulation tool, pole zero analysis, and check whether we get reasonably matching results. Go back to the schematic and run pole zero analysis. If you already have it, generate the plots.
Go to results. No,
Go to
no
results. Go to results.
report, main form.
Main form.
PZ, select PZ. Yeah, plot.
Plot. Down. Okay. All right. So just look at the locations of the poles. Just zoom in there. You can actually put markers. You can zoom in, put markers. Okay. One more to that. Okay. So as you can see here, these are real poles, and the first pole actually is at a frequency of 27.15 megahertz, right? Okay, so let us go back to that spreadsheet. Yes, where is that? Omega P1.
22 megahertz. FP1.
FP1. We computed actually here from those values reported as 22 megahertz. What actually we get the location as about 27 megahertz. So that actually matches. Very good. Similarly for FP2, can you just look up there?
0.9 gigahertz. Here it is 1.
Here actually it is 1 gigahertz, and there actually it is 0.9 gigahertz, which again matches. Look at the zero frequency.
131 gigahertz. Down.
Okay. So look up there. Go to 0. Put a marker. That was good. 126.9, 127 gigahertz. So you actually get to see that there is a pretty good match between our estimates, our design approach, and the results actually that we are seeing. All right. So that is the illustration of the GM over ID technique for two simple circuits. One actually is the simple common source amplifier with the NMOS device as the active device with a resistive load for a design set of specifications which focus on the desired gain, the small signal DC gain, right? And then the same circuit modified to achieve, to get a common source amplifier with one more transistor, the PMOS device actually as the current source load. Having done this, let us next move over to the design of a complete 7-pack op-amp at the schematic level, right, using the GM over ID technique. So can I just go back to those specifications?
Yes, yeah. Naveen, go back to the slide. Next.
Go for this.
Yes.
Okay, I'll just go for slide presentation. All right, so the specifications actually we have is supply voltage 3.3 volts, non-zero DC gain equal to or greater than 50 decibels. Total power consumption is 50 micro watts. Is that correct, Sijo?
Yes, sir. Yes.
Okay, and then balanced output swing, that is actually final output to do that. Unity crossover frequency equal to greater than 10 megahertz for a load capacitance of 10 picofarads and a slew rate greater than 10 volts per microsecond. So these specifications are reasonably good and practical op-amp specifications. We have not listed other specifications such as the noise figure, etc. The settling time, lots of other things are there. We have kept it relatively simple right now to illustrate the design flow. So let's get started. So Siju, you would like to take over?
Yes, sir. Yes, sir.
I'll actually get an opportunity to rest my throat for some time.
Yes, yes, sure. Yeah, so here the design specification as given. So from the power consumption rating and the supply voltage, we are getting an ID value of, Navin, can you open a spreadsheet, please? Blank. Blank one. Add a sheet maybe. Yeah. So I will list out the values here for cross checking finally. So ID value we are again getting as 300 microamps. So ID equal to 300 UA microamps we are getting. Okay, and CL is already given from the specification as you can look at. It is 10 picofarad. Okay. Yeah. So unity gain bandwidth, it is given as 10 megahertz greater than or equal to UGB. Yeah, 10 megahertz. So the equation for the unity gain bandwidth, that is basically GM1, that is GM1 is the transconductance of your input device, okay, that divided by the CC value, that is a compensation capacitor value. So Naveen, can you just show that schematic once, then it will be helpful in the slide itself maybe. Yeah, so this is the basic 7-pack op-amp uh, design. Okay, so I'm going with the same naming convention. So if you open the tool, here the compensation part is not shown. So Naveen, can you open the schematic on the tool op-amp? Seven, yeah, schematic. Yeah. It's fine. Okay. Can you zoom it? Yeah.
Yeah, just a close off.
Let it be there. Let it be there. Simulations. Let it be there. Curves we need. Yeah. So if you look at the schematic, this is the 7-pack op-amp design. Okay, along with Miller compensation. Okay, and I have a pole cancellation resistance also as attached. So the compensation capacitance, I'm naming it as CC, and I have a load capacitance of 10 pico. Okay, so by the rule of thumb, in order to get a phase margin for a two-stage op-amp, okay, in order to get a phase margin of 65 degree, okay, as a rule of thumb, okay, we can find that compensation capacitance value is almost 2.22 times CL value. Okay, so that ends out to be, if load capacitance value is 10 pico, okay, 0.22 times that CL value will be my compensation capacitance value. So for the first cut approximation, I can consider the CC value as 2.2 picofarad, okay. So if you go back to the spreadsheet, okay, yeah, so CC value, from CL value we can find it as 0.22 times CL, that is CC is equal to 2.2 picofarads. You can derive the same, okay. You can look at the phase margin equation, okay. So this value is computed by, for a phase margin of 65 less than or equal to 65 degrees, you can write the equation for the phase margin. So considering for this two stage op amp, okay, we can write it as 180 minus the phase margin equation turns out to be 180 minus tan inverse of your unity gain frequency divided by your dominant pole, that is omega p1, minus tan inverse of whatever the unity gain bandwidth divided by the non-dominant pole, minus tan inverse of omega UGB by omega z. So if you substitute the values here, taking into consideration that your zero frequency is a decade away from the unity gain frequency, okay, so you can find the value for, okay, CC, okay, in relative to CL for a phase margin greater than or equal to 65 degree. You can just substitute the consider the phase margin equation, and if you substitute these values, you can come to the relation that CL value, okay, that will be equal to 2.2 times my compensation capacitance value. So that is how we reach to this value. So CL is 10 pico, so 0.22 into CL turns out to be C compensation capacitance value turns out to be 2.2 picofarad. Now the slew rate, Naveen, can you type slew SR? Okay, I'm denoting it as SR. So the slew rate from the specification, it is given as 10 volts per microsecond. So it will be 10 volts per US microsecond. So from that equation, the slew rate equation is basically, it will be equal to that whatever the tail current value divided by CC. Okay. So what is the tail current value? Tail current value I can find. We know the slew rate, okay, and we know the compensation capacitance value. So slew rate is equal to tail current divided by compensation capacitance value. So now tail current you can find it at slew rate into whatever the compensation capacitance value. So if we know the tail current, I tail value turns out to be 10 volt per microsecond into whatever the CC value, that is a 2.2 picofarad, that comes out to be 25. You can write the value directly, Naveen. It turns out to be 25 microamps. Okay, now we have the unity gain bandwidth as 10 megahertz. So from the unity gain bandwidth equation turns out to be GM1 divided by CC. So from that equation, we can find GM1. GM1 is equal to whatever the unity gain bandwidth into your compensation capacitance value. So unity gain bandwidth here it is, from the specification it is 10 megahertz, that multiplied by your CC value, that is a 2.2 picofarad. So that turns out to be G1 value comes out to be 150 microsiemens.
So into 2 pi.
Yes, sir. Yes, sir.
Into 2 pi. Yeah.
Yes.
Because hertz.
Yeah. In hertz, it will be 2. So that turns out to be 150 microsiemens. So now we got GM and we know the ID value. So ID value, that is the I tail value we got. That is the total I tail value is equal to the ID1 plus ID2. So if you go to the schematic, Naveen, can you show that schematic? Yeah. So here, if I denote input stage, Naveen, can you zoom to the input stage? Yeah, fine. So whatever the current flowing through the transistor NM1, if I denote it as ID1, and whatever the current flowing through NMOS NM0, that is input transistor on the right, as ID2. Since we are considering the identical conditions for the ease of calculation, we can denote the current flowing through, okay, each half of the circuit is equal to ID1 is equal to ID2 is equal to ID. Okay, then whatever the tail current that is flowing through NM2, that is flowing through the tail transistor, turns out to be 2 times IDD. So the tail transistor, whatever the current I tail, that value we got from the slew rate specification, okay, as 25 microamps. Okay, so from that we can find what is the ID flowing through each transistor. So that will be 25 microamps divided by 2, that will be equal to 12.5 microamps. Okay, so in the spreadsheet we can put the value for ID as 12.5 microamps. Yeah, so now we got the values for GM and ID. Now we can calculate what is my GM by ID ratio. So if you calculate the GM by ID, GM divided by ID, okay, so that value turns out to be, what is the GM here, 150 divided by whatever my ID, 12.5 microns, that turns out to be 12. Okay, so the ratio we got it as 12. Okay, now we know the unity gain frequency value. Okay, that is given as 10 megahertz. So in the top it is given as 10 megahertz. So from taking into consideration that we are designing the circuit so that my zero frequency, that is the right half plane zero, that is omega z, okay, that location that should be at least a decade away from my unity gain frequency. Okay, so omega z, okay, will be 10 times a decade away from my unity gain frequency. So that is almost 10 times my unity, that is 100 megahertz. 10 megahertz is my unity gain frequency. So omega is that we are trying to put a decade away from a unity gain frequency. So that comes around 100 megahertz here. So from that one, we know the omega z value. Okay, so omega z equation turns out to be GM7. So if you look at the schematic, Naveen, can you look at the schematic? Yeah, go to the top. Yeah, finalization. Yeah, so whatever the PMOS, the input active device at the second stage, okay, so that GM7 divided by whatever the compensation capacitor. So here it is PM2. So that whatever the GM of this PM2 divided by the compensation capacitor value, that will give you the omega z value. Okay, so this omega z we are trying to push at least a decade away from my unity gain frequency, that is 10 megahertz. So from these values we know CC value. Okay, so we are finding what is the GM of this PM2. So that value we can find it as whatever the omega z location, that is 10 times the unity gain frequency location, that divided by whatever the CC, that is a compensation capacitance value, which is 2.2 pico. So that gives GM7 around 1.5 millisiemens. So GM of PMOS, yeah, that's fine, 1.5 millisiemens. Okay, so if you apply the now we got the GM value here. Okay, so if you go with the same GM by ID ratio for the second stage MOSFETs also, so GM by ID ratio we already found it as 12. So from that one we can find what is the ID which is flowing through the second stage. So if I put ID second stage, ID underscore second stage, we can find it as whatever my GM by ID ratio we already know. So from that, which is equal to 12. So from that one, we can find ID will be equal to 125 microamps. So for the first stage, it was 12.5, right? But here, but there the GM of my input transistor, that is a GM1 or 2, which was comparative 10 times lesser than the GM of my PMOS here, because we took into consideration that we are pushing my omega 0, that is right half plane 0 location, at least a decade away from my unity gain frequency, so stability concerns are taken care of. So since GM has gone of the second stage PMOS has gone 10 times higher, obviously your ID value will also go up, so that your GM by ID ratio remains the same, that is equal to 12. So ID value we get it as 125 microamps. Okay, so now we can actually find what is the, now the aim is, here also we are keeping the L as minimum, okay, for in order to get a maximum bandwidth. And now we can find what is the W value from the current density versus GM by ID curve, which we already generated from the MOS characterization. Okay, so we can look into that MOS characterization and we can plot the GMI ID, that is equal to 12, what is my current density value, okay, and from that one we can find W of the MOSFETs for each stage. Okay, for first stage and for second stage, okay, we got what is the GM by ID value remains the same, we got what is the ID value. Okay, so from that one we can find what is the current density and correspondingly what is the W for transistors in each stage. Okay, so that is what we are going to find. So here also we are keeping the MOSFETs, okay, in moderate inversion. Okay, so let's look at the plots. So we can go to the tool and see the NMOS characterization setup. It is the same thing as ever we have done for the previous two designs. The characterization setup remains the same. Naveen, can you open the schematic? Yeah, NMOS NMOS. Okay, load the curves basically. Go to ADXL window from the library manager. We already have the curves available, so we can just load the state. Okay, here the results are already available. You can go to plot all. Okay, okay, so we can just see what is the current density value for a GM by ID of 12. So for that we need to plot GM by ID. So can you plot GM by ID in a separate window? Yeah, now I need current density. So current density is again ID by W here. So whatever the analysis we did, it remains the same here. So once the characterization is done for a set range of values, then we can make use of it for all the designs. Okay. So W value is here again 5U. So 5U, that gives you the current density value. So if you plot that curve, yeah, yeah. Now we can plot current density across GM by ID. So GM by ID curve is already available. No, it is already there, Navi. Window 35. Yeah, paste it here. Yeah. Yeah. Now we have GM by ID and current density across VGS. Now we can go to current density across GM by ID. Okay. New window. Okay. So GM by ID, we got it as 12 here. So if you put a vertical cursor at 12, yeah. So we are getting a value around 20. Okay. So if you go back to the spreadsheet, we can now note down the current density value for the input stage. It's ID by W. ID by W1. W1, that is for the MOSFET we did. So for the NMOS we did now, for the PMOS we need to do separately. So it is 20 now. Okay. So now from this we can find what is the width of my input MOSFET, right? That is width of M1 and M2. So W of W1 and 2, 1, 2, which turns out to be ID value we know, ID by W also we know. So ID value is 12.5 microamps and ID by W is 20. So from that W1 and 2 turns out to be 0.625 micrometer. Yeah. So we got the value for input MOS. Okay. So now we have another MOSFET. If you look at the schematic of the 7-pack op amp, schematic, yeah. So we got the value for M1 and M2, that is the input transistor width we got from the curve from current density across GM by ID as 0.625 micrometer. So since we already have the curve for NMOS, now we can find the MOS width at the second stage, that is which comes as the load of the second stage. So Navin, can you show the second stage of this schematic? Yeah. Yeah, we have one more NMOS here. Okay. So we can find what is the value of that. So if you go back to the curves again, that is current density across GM by ID, which we plotted now.
Yes, Joe. The GM over ID value remains the same. The
Yes.
current density also remains the same, but the current value is 10 times that of the current for the input transistors.
Yeah.
So as a result, the width turns out to be equal to 10 times.
Yeah. So if you divide that current density 20 divided by your current we already got. Okay, you can see in the spreadsheet as 125 microamps. So if you divide that current density by this, we will get it as 6.25 micrometer. Okay. Yeah. So now we can look at the PMOS caravans. Okay, and we'll. Okay, so from this curve itself, 1 minute, Naveen. We have a tail transistor that is again NMOS. Okay, so there also the GM by ID value that remains the same as 12, but ID value changes, that is double the what are the ID value you got for the input MOSFET. So for the input MOSFET, that is M1 and M2, your ID value was 12.5 microamps. So the I tail value we already got double that of, that is 25 microamps. So from that one you can calculate the W for the tail transistor also. Okay, so that turns out to be double the value of your input MOSFET. Okay, so now we look at the curves for PMOS and we will set up the W value for PMOS also. Okay, so again you can do the same exercise. We have to plot the current density across GM by ID. So GM by ID remains the same. So Navin, can you quickly plot that? View results. View results. Right click on the interactive. No, click out. Yeah. view results. Okay, so we got the plots. From this one we can plot current density. We need to plot first. Yeah, we'll go to the ID, we'll send it to a new window, the same exercise we did. Can find the current density from the calculator. Yeah, so we can plot current density across GMO, right? Okay. Okay, so GMO ID remains the same as 12 here. So we can find what is the current density for that. Yeah, that comes around 5.27. Okay, so the current density for the PMOS mirror load. Okay, so that we got it as 5.27. That is the current density for the PMOS, right? So from this one, now we can find, we know the ID, right? The ID flowing through the PMOS in the first stage, that is through the mirror load, that will be same as the current flowing through your input MOSFET, right? So ID remains the same and GM by ID also remains the same. So current density we got it from this curve as 5. So if you calculate the W here, we will get it as 12.5, that is the ID value divided by whatever the current density value here, that is 5.27. So that turns out to be 2.2 micrometer. Okay, so Naveen, I think we can update the values in the spreadsheet and move further. Yeah. So for the tail transistor, W tail, GM by ID remains the same. ID turns out to be double. So obviously width also turns out to be double. So it will be 1250 micrometer, right? Doubles of 625 nanometer. So it will be 1.25.
Now it is 1.25 micro.
Yeah. Okay. Now for the mirror load, so we can just see the transistor number there for the PMOS. In the schematic, look at the PMOS number there on the top. Yeah, so it is PM1 and PM0. So W1 and 1 or 1 comma 0, we are getting it as 2.2 U, right? We got the current density value is 5.7 and current we already know 12.5 micro. So 12.5 by 5.7, that is W of PMOS, W underscore PMOS 1 2. Yeah, that turns out to be 2.2 U. Okay. Now we need to find it for the active PMOS device, that is comes in the second stage. Okay, so there GM by ID value again remains the same. Okay, and current density value also remains the same. Okay, but ID value is changes here, so it is 125 microamps. So you can calculate the W from that value, that turns out to be 25 micrometer.
23.5.
Yeah, 23.5 is the exact value we are getting. We'll approximate into 24. 25 micron. Yeah, I think we forgot to put one more value, that is the NMOS load at the second stage, width of the NMOS load at second stage, WN second stage. Okay, there also the GM by ID remains the same, but current is 10 times of the first stage. So obviously width also will be 10 times of W1 and 2, that turns out to be 6.25 micrometer. W1 and 2 we already got, you can see 4 rows. On the 14th row it is 0.625 micrometer. So omega n second stage is 10 times of that one, because GM by ID remains the same, but ID increased to 10 times. Why? Because we took that taken into consideration that we are pushing our right half plane 0 a decade, at least a decade away from my unity gain bandwidth. That is how we reach that to that increased ID value, because the GM increase for the PMOS, that is input device there, so correspondingly ID also increased there. Okay, so now we got all the values from the GM by ID technique. We got all the values for all the MOSFETs in the 7-pack op amp. Okay, we already know the compensation capacitance value also. Okay, so now we can go to the schematic. Okay, we can give back put the values here. We already have cooked up the schematic here, so once again we can cross check all the values are right. Okay, so now you can go to the simulation. Sir, anything you want to add, sir?
Yes, Joe, you have to calculate, talk about the zero knurling resistance.
Okay, okay, yes, sir, yes.
So for that, first carry out a DC operating point analysis.
Yes, sir, yes, sir. So we already have the saved state available. Yeah.
So can just load it. So it's again the same. We are first of all doing a DC operating point analysis. We do all analysis simultaneously, but we first look at operating point results to verify whether all transistors are in saturation region, that is region number 2 at all or no. Maybe please check corner also.
Yes.
Yeah, we can come to the schematic. Naveen, you can come to the schematic one. Yeah, go to view, annotations, setup. So what we are trying to do is we can print the maximum 5 DC operating parameters in the schematic itself. So it will be better to analyze from the schematic itself. So if you can choose the library, which library you are doing. So there is GPDK 180, and which cell you want to highlight the DC operating parameters. So we are going with PMOS first. So we can come down for the component parameter. Instead of that one, you can double click on the component parameter column. Now onto the left. No, onto the left. Component parameter, you double click. Yeah. Make it as DC operating point parameters. Now it is highlighting component parameter in the schematic. So instead of that one, we are highlighting DC operating point. So double click there. You can choose region of operation first, REGN. Yeah. Then
Again on the left.
On the left, change the component parameter to DC operating point. Yeah, GM, let it be there. DC operating point parameter. ID, make it as ID.
Type ID.
Type ID, fine. Yeah, that will be fine. That's fine, that's fine.
VGS is not required. Only SAT is required.
Yeah, VD SAT, you can double click there. VD SAT. Yeah, apply. Yeah, now go to change the cell to PMOS. No, wait a minute. Yeah, change it to NMOS. We want it to get highlighted for NMOS also.
DSAT. Apply settings to all.
Yeah.
It's done.
Yeah, if you zoom into the MOSFET, you can see. Yeah. So ID value, can you zoom to the M1? Yeah. So ID value, we got it. We designed it for 12.5 U. We are almost getting that 12.89 U. A region of operation, you can check first. So all are in region 2. That's saturation. You can also check the I tail value for the bottom. It's on region 2, and we are getting ID of around 25.5 U. Yeah. You can also check the second stage. We're getting slightly higher. We did it for fun 25 U. Can you go up, Navin? Yeah, all are in region 2. So now, yeah, there also you can.
Okay.
Yeah.
So now look up the value of transconductance for the second stage PMOS active device.
Yeah.
That is 1.725 GM for PM2. Okay. So what actually we are trying to do now actually is to compute the value for the zero nulling resistance, which is connected in series with the compensation capacitance in the schematic. Can you slightly zoom out of there, Naveen? Okay, so you can actually see that. No, not too much. Go back to the previous one. Good enough. So can you move your cursor across C1 and R0? Yeah. So C1 is the compensation capacitance, right, resulting in Miller compensation, and R0 is the zero nulling resistance. So the whole idea is very simple up here. The compensation capacitance C1, whatever value you specify, gets magnified by the gain of the second stage and appears as a Miller capacitance across the output port of the first stage, generating a large capacitance as a Miller effect, and therefore resulting in a large value of a time constant, and therefore inserts a dominant pole. Now, when it actually also does this, it does one more thing which is not very desirable. It prepones or advances the RHP0 to a lower frequency, because the frequency at which the zero occurs in radians per second omega z, right, is GM of PM2, that's the second stage active device, divided by the compensation capacitance value. So larger the value of this capacitance, right, what I end up finding that for a given GM value of PM2, the second stage PMOS active device, right, smaller will be omega z. The problem is this zero happens to be a right hand plane zero in the S domain. So while in magnitude plot, it does produce the desirable effect. In the phase plot, the phase generated by this zero, RHP0, will be negative, and hence it degrades the phase margin drastically. So what actually we now do is we recognize that the RHP0 basically comes into picture because of this compensation capacitance. And the effect of it is to couple the input node of the second stage to its output node. So if I can minimize this coupling, feed forward coupling to this compensation capacitance between the input and output node of the second stage, then that actually helps. So how do I minimize the coupling? Now, what exactly I mean by coupling? The feed forward coupling, what exactly I mean is that if the output pin of the first stage changes in potential as a function of time instantaneously, that is immediately instantaneously coupled to the output pin or output node of the second stage by C1, the compensation capacitance. This is so because we do not know how to change the voltage across a capacitor instantaneously, because it would require us to supply large terminal current to the capacitor. So to minimize this coupling effect, whatever change in voltage occurs at the first terminal of C1, that voltage change, a large chunk of it, if it is dropped across a resistance, so that change in voltage across C1 per se is minimized, then our job of minimizing coupling is taken care of. And that exactly is what we actually end up doing by connecting a zero nulling resistance in series with C1. To be very specific, when you write the transfer function, right, we have the frequency at which zero occurs, right, as Gm of Pm2 by C1, that is Cc, the compensation capacitance, right? If I bring that Gm to the denominator, I get it actually as 1 by G. Actually getting a DC gain of 56 decibels. The design spec actually was equal to greater than 50 decibels. And gain bandwidth product, omega E here.
Yeah, now you put a horizontal case at unity 0D.
Some background noise. We wanted 10 megahertz, right, C2?
Yes, sir. Less.
Getting larger.
Yes.
Have we connected the capacitance correctly? Load capacitance? Just check in the schematic.
Yes, sir.
Okay, that's good enough.
Yes.
So we are actually getting about 56 decibels gain, DC gain, and about 55 megahertz of gain bandwidth. All right, so that's the performance of this particular operational amplifier. So with this, we have illustrated as to summarize the complete schematic design using the GM over ID technique for a 7-pack operational amplifier, including its compensation and zero nulling. Right? So I will actually take the questions once I summarize the day's activity. Right? We have overshot the time by 10 minutes, going my time on my laptop, 10 past 4. Right? So we actually started with setting the perspective for analog, also giving application perspective in the morning. Then in the first session, we developed and evolved the circuit topologies for various amplifiers, starting from the basic gain stage, then modified that to a common source amplifier with resistive load, then to the common source amplifier with a PMOS type source load.
Participants, please keep yourselves on mute. We are hearing lots of background noise.
Okay, and then what actually we did is to look at the differential signaling and build up the differential amplifier. And then we looked at the 7-pack op-amp. Followed by that, in session 2, we developed the idea of design flow based on the actual design variables and device parameters of interest to us, rather than some hypothetical parameters such as mu into C ox, then W by L, and all those kinds of stuff, as is applicable to longitudinal device theory, which anyway hardly holds good for advanced nodes. And therefore, we came up with the presentation and illustration of design of common source amplifier with a resistive load, as well as the PMOS current source load, using the GM over ID, or transconductance efficiency methodology of designs, by first characterizing the devices to generate lookup traces and lookup tables, right, for the transconductance, FT, GM over ID, self gain, and the capacitances of the MOSFET, which are of interest to us, right? From basically the gain and the frequency response point of view, we actually could have generated and looked at curves which are of interest to us based on either noise figure or power dissipation, etc. So in the end, we are relating everything to the GM over ID technique, right? This actually will take up some paper and pencil workout to actually how to relate these things and figuring out how to make use of that technique. So this technique actually is pretty universal, goes across technologies, because everything actually is based on the characterization results, right? And then we extended this particular result by also showing, I mean, we also illustrated the hand calculation and the cross verification of this in the simulation for the common source amplifier with a PMOS current source load, and found a pretty good match, right? So what we then did is to go and extend this technique, right, for the complete 7-pack op-amp, and also illustrate compensation and the stability analysis. So that has been the activity for today, right, as was set forth right in the morning, right, as the coverage and the scope, right. I do hope, along with my team, Sijo and Naveen, that the day actually has gone good for you. It has been productive, right. We are open to your critical feedback and queries as well. Rathod, sir.
No, it's okay. It's very nice, sir. But
Sir.
nicely they have demonstrated everything.
Yes, sir.
Sir, I have few doubts, sir.
Yeah, please.
Yeah, please.
Sir, in this GM by ID technique, the gain mostly can we design for a specific gain? Here, the gain specifications were quite vague, like greater than 5 or something like that. Can we design it for a specific volume?
We can. It actually requires large number of these characteristics curves to be generated first of all, and then maybe a couple of iterations.
Okay. And one more doubt, sir. While we were designing the common source amplifier, while doing characterization, we have fixed the VDS to 1.65, which was half of 3.3. But while we were doing the op-amp MOS characterization for a op-amp, what is the VDD used there? VDS used there?
Same. Actually, have used the same set of curves.
But again, while operation, the tail current and the active device of NMOS will have a different overdrive over them.
It is not for the overdrive. It is basically like, there the idea behind keeping the voltage VDS as VDD by 2 is based on the fact that these small signal parameters of the MOSFET are not strong functions of drain to source potential.
Okay.
They are weak functions of drain to source potential.
Okay. So that is not going to matter if we choose.
It will, because there is a dependency on VDS. So if you want to do exact designs, then you need to generate curves for different values of VDS also, which I already mentioned when I talked about approach.
Then can we do a separate characterization for this tail device using a different VDS, which is more appropriate?
No, what I meant actually is when you are characterizing the devices, right?
Okay.
from a foundry PDK. All right.
Okay.
What actually we do is we parameterize WL, fine, over different assorted discrete sets of values of bins.
Okay.
Okay. And for each bin, we generate for all these parameters as functions of gate to source voltage, right?
Okay.
For different values of source to bulk potential difference, for different values of drain potential difference also.
Okay. Okay, sir. Okay.
I have a huge set of data, so I can look up. And if I find that I need to generate little more, then I take page to generate it.
Okay. Okay, sir.
Did I answer the query?
Yes, sir. Yes, sir.
Yeah.
Thank you.
Anyone else wants to ask something? No, sir. I don't think there are any. Hello. Yes.
Yeah. Shala madam is there. Shala madam is there.
I have.
Yeah. She's there.
Is there. So, madam, do you have any queries?
Yeah, I do have a doubt. Doubt in the sense, is it a thumb rule to keep L equal to whatever is the technology parameter for analog devices?
No, madam. No, madam. If I need large gain, then I actually require a larger value of R out
Yes.
for my active devices. Therefore, right, I choose larger values of L. So L can be 2.5 times the minimum or 5 times the minimum.
So in that case, even if larger gain, larger length, then bandwidth also will be larger, no?
No, larger the gain, bandwidth is smaller always.
Okay, okay. UGB, it is basically bandwidth, again, bandwidth product. Yes.
Yes, the gain
Yes.
bandwidth product.
Okay. So
Right, so if I need
L also needs to be iterated like this?
It depends, like, if I need large bandwidth, right, in my interest, then I try to keep L closer to technology minimum. I make a choice.
But isn't then L equal to just 250 nanometers and W equal to 20 or 10 microns is something which is having a small length and very wide. So, yeah, I mean, short channel effects will come into picture there then.
Short
And that is why.
that is fine, but in analog, like anyway, I require large bits, devices to be large. My choice of L essentially depends on whether I want large bandwidth or small, large gain. So I need to take a call. So I may want to iterate.
Okay.
That's the reason why we actually parameterize W and L, and that is a huge set of data and huge set of curves.
Was the previous approach was only characterizing for GM or ID and then decide L and W, and something like, I think that L is some 5 times of technology parameter. That was the thumb rule used in industry. That was our impression. Is that correct? Is this the reason?
No, it actually can be done. That's a rule of thumb. Basically, to keep your R out for the transistors large enough.
Yes. So gain will be larger.
So the gain will be larger. Fine, right? So that's all the intention actually is. It is not a hard and fast, a must kind of a stuff. That's a general approach. However, right, if the bandwidth required is large, then
L should be
L should be small.
Okay, sir. Okay.
So it's a designer's choice. As I said, like in the morning, for every set of specifications, right, we actually end up designing 3 variants of the circuit. And we tape out all 3.
Yes.
And then look at which one works best.
Okay.
And typically for critical applications, we pick the best one.
Yes, definitely.
Yeah. So it is iterative, right? Because devices are so complicated.
Yes.
And because our simulation results actually can vary, differ from our hand calculation estimations by as large as almost 30+%.
How good the matching is there between these simulation results, maybe after post layout, and then the actual devices?
If we have actually done our iterations correctly and we have reasoned out what's happening, right, the match is very good.
Okay.
The match is very good. It actually comes to like anything within 10% is good.
does it give a pessimistic result simulation, that is everything will be better than what we get by simulation, so we are damn sure that yes, it is going to work?
Yes, the simulation results, if we can make it conservative. Okay, let me give out a trick.
Okay.
What is called the trade secret. Even in real designs, right? As I said, we actually do at least 3 different designs for the same set of specifications.
Okay.
The
It was
performance
nice.
is matched. All right, but then what actually we end up also doing is, while putting up the data sheet, right, we go further conservative. So what actually we do actually is, let us say, gain bandwidth I have getting pakka even on silicon tested, right, or in my simulations also, right, something like 100 megahertz. But in my data sheet, I specify it as maybe 80 megahertz. So I'm actually acting safe.
So if at all you have to go for 3-stage operational amplifier, you have to take care of the phase margin perhaps.
Obviously, yes. And even in this case also, you might have actually observed, madam, we have used for simulation ideal stimulus sources. So honestly speaking, simple op-amp of this nature, just 2-stage architecture also, right, must be modeled with 3-pole transfer function and not 2-pole transfer function. We have not done that here in the simulation setup. We have used ideal stimulus sources. If I include the stimulus resistances, then I actually end up getting the 3-pole transfer function.
Okay, sir. It was very nice. The entire was hectic also. It's good.
Yeah,
Thank you,
sir. Nathur, sir.
Yeah. Thank you, Kulkarni sir. Thanks a lot.
Yes, sir.
Yeah. And thank you, Thomas sir. Thank you very much. You tried your level best in spite of having a lot of connectivity issues. And since Naveen was with us, that's why we could you could able to manage actually. So thanks to Naveen also.
Oh,
yeah.
Thank you, sir.
Yeah.
Thank you.
Yeah. And we will meet tomorrow morning, 10 o'clock, right?
Yes.
Rathod, sir, my
Yes, sir.
availability tomorrow is little doubtful. I'll attempt, at least for some time.
Okay. Thanks.
Maybe only for the first session, for some time I may be able to join.
Okay, sir. Okay.
Yes, sir. And subsequently, Sijo and Naveen actually would continue.
Okay. Thank you. Thanks.
Thank you. Thanks everybody. Thanks for your patience.
Thanks. Thank you, everyone.
Thank you. Yeah.
Thanks, Naveen and
Thanks.
Thanks, sir.
Yes, sir. Thank you.
Thank you, sir. So participants, as usual, you will have a quiz tomorrow morning. Few questions I'll set. 10 questions. Morning 8 o'clock. 8 o'clock to 10:30. Please appear. It's just a basic questions, basic understanding. Nothing else. Nothing so serious. But you must appear for the examination, please. Okay. And feedback form is also there. I have put the link. Please, feedback form, come attendance sheet. Please fill. Those who are not filled up.